Hi everybody, welcome to the next lesson on friction. I really like this picture that you see right now. This is just a demonstration of how important friction actually is in our lives. We sometimes think that friction is a bad thing. Friction causes heat, it causes things to wear out, but in fact we need friction to do everyday things, such as walk around on a surface, hold a pen, even turning a page. All these things are positive examples of friction. So try to keep that in mind as we're going through this lesson. Now, we're just going to go through the definition of friction. And remember, friction is the force that really opposes the motion of an object when two surfaces are in contact. That's really important. You need to have two surfaces. It could be a variety of surfaces, it could be the air, but you always have two surfaces in contact. And we're going to be looking at what happens when we've got objects resting on a horizontal surface. We're doing at angles and other surfaces in grade 12. Now, the whole reason we have friction is because of roughness in surfaces. When you look at any surface at a microscopic scale, even ones that seem very smooth are actually quite rough. So it might look something like this. You have a lot of roughness, some inconsistent patches. That might be one surface, and here's the other surface. So very similar again. We've got a lot of roughness associated with them. And what happens is, as these surfaces are dragged across each other, there's quite a bit of friction or energy being lost in the form of heat as these surfaces are trying to get across each other. The other thing that happens as well is at a molecular level, you see here in this diagram here, you see that the atoms of one substance are attracted to the atoms of another substance. So we have quite a few intermolecular bonds or weak bonds, but there's quite a few bonds occurring. And they cause surfaces to adhere, such as the surface of the saran wrap over here adhering to the glass. So we also have to remember these intermolecular bonds between various surfaces. So I'll label these as intermolecular bonds. They're temporary bonds. They only form for a few moments, but they're enough to, in addition to roughness, to hinder the motion of an object. Okay, now, when we look at motion, you probably already realize that there's two types of friction that affect motion. So the first type of friction is static friction. This is friction that affects objects that are not moving. So you're trying to get something to move in the first place. And then there's also kinetic friction. This is the force that's opposing the motion of objects that are already moving. And you probably realize this already, but when you have an object you're trying to move, it takes a lot of force. But once it begins moving, it's a little bit easier to move. This means that the amount of static friction is much greater than the amount of kinetic friction. It makes sense if you think about the microscopic irregularities and intermolecular bonds between the two surfaces. When the two objects are, or surfaces, sorry, are close together, the object is not moving, the intermolecular bonds have a little bit more time to form, and also the irregularities are embedded in each other. So it's quite hard to initially move the object. Now what happens is, as you're actually beginning to move, once you overcome that static friction, the surfaces can slide past each other a little bit easier, and those intermolecular bonds do not have as much of an opportunity to form either. So again, kinetic friction is always lower than the initial static friction trying to get an object to move in the first place. So keep that in mind when we're doing these problems. So what we're going to be doing is looking at an example, and we've already done this in class, of moving a textbook with a mass of 1.3 kilograms across a desk at a constant velocity with an applied force of 4.3 newtons. Because we're moving at a constant velocity, we know that I'm not going to have an acceleration. So my acceleration is 0, which implies that my F net must be 0 as well. So my overall force acting on the book is 0, even though we're moving. So keep that in mind. It is possible to move and still have no net force. Now, the interesting thing is I have to apply a force to keep the book moving. So when we look at the actual forces acting on the textbook, I know I'm going to have my applied force And in this case, my applied force is 4.3 newtons. Now that applied force is just enough to overcome friction. So friction is acting in the opposite direction. So force friction. So it must be equal and opposite, give me an F net of 0, so it'll be negative 4.3 newtons. And it's important to recognize when you're doing this lab that when you're measuring the force with the spring scale, you're actually not measuring the friction force, you are measuring the applied force. But because we're dragging the book across the surface at a constant velocity, the applied force happens to equal the force of friction acting on the book. Now, other forces that we have here are going to be the force of gravity and also the surface force or the normal force acting on the textbook, and those two are also equal to 0. So basically what happens here is the book is being moved across nice constant velocity, no acceleration overall. Now the next question was, what would happen if the applied force was no longer exerted? What would happen to the moving textbook? Well, let's take a look at this. So we draw a free body diagram of the textbook now without the applied force. We're still going to have gravity and normal force. Again, they are opposing each other on the horizontal surface, so they're going to cancel out. And we still have friction because we're moving. So that force of friction will still be there. And that force of friction is going to be 4.3 newtons backwards. However, because I don't have an applied force, we actually now have a net force. And the net force happens to equal force of friction. So the sum of the forces, or the F net, is going to equal to the force of friction in this situation, which equals 4.3 newtons backwards. So in other words, I'm going to be accelerating backwards negatively. And since I was moving forward or positively, I'm going to eventually come to a stop. So accelerating negatively, coming to a stop. And it makes sense. So you notice that as well. When you stop dragging on your textbook, or not pulling on the textbook, it came to a stop. And we can actually look at an applet. This is one of the applets we have linked on the website. And we see here we have an individual who's going to be pushing a refrigerator, quite large refrigerator. And you can keep track of the forces with little arrows here. So let's take a look what happens. So if I apply a little bit of force, you notice that the friction force is going to equal the applied force while the object's not moving. So whatever I try to do, the friction is going to oppose me. So that's static friction. Now eventually, once I get this moving, we're going to have kinetic friction. And you can see here that my applied force is larger than the friction force, so I'm accelerating. You see the green arrow represents the F net. So I'm accelerating forward. Now if I apply a force equal to the friction force, we don't have any kind of acceleration. The object's moving at a constant velocity. And when I stop pulling, the only force acting on the fridge is friction, and it quickly comes to a stop. Again, this is exactly what we saw in this particular part of the lesson. Now the next part is this. What would happen if the textbook was placed on a rougher surface? And so what would happen to the forces to maintain a constant velocity? Well, it makes sense that if I'm on a rougher surface, I'm going to have a much larger friction. And the friction is going to be due to the roughness, most likely, but also the intermolecular forces. So in order to overcome that, I'm going to have to apply a much larger applied force. So friction and an equal and opposite applied force. So both of them are quite large. Remember, we still are going to have gravity and the normal force, but because of the same textbook, they're going to remain unchanged. So in this case, what happens is we have to pull with a much greater applied force to overcome greater friction. Now, what would happen if I go back to the original situation and now instead of one textbook, have two textbooks? So I have to move two textbooks across with a constant velocity. It makes sense that if I've got double the mass, I'm going to have most likely double the friction. So my friction is going to be larger because of that extra mass. And what happens then is I have to have a correspondingly larger applied force. So I'll probably have to pull harder. And you see this everyday situations. Try moving a small pole versus a large boulder. Much, much harder to move the boulder because, again, of the increased friction. Now, unlike before, because we have additional mass, my force of gravity is going to be larger, and so is my normal force. So that's a little different than before. So again, we've got larger mass, so therefore more gravity, and as a result, normal is larger as well. So let's take a look at a situation we're going to be looking at in a mini lab where we are going to investigate the effect of increasing mass on the force required to move a textbook across the table. In other words, the effective mass on the force of friction. So that might be a good title over here. So the effect of increasing mass, so increased mass on the force of friction. So we're going to try to keep everything constant except for the mass. So the textbook's going to be the same, the surfaces are going to be the same. So we're going to be looking at our textbooks. We'll do this as one textbook, then 2, 3, 4, and 5. Again, we did this in class. And let's make a little bit of an assumption that each textbook has a weight of 11 newtons. So if I've got one book, it's 11 newtons. 2 books are going to be 22, 3 are 33, etc. And because gravity and normal are going to oppose each other on a horizontal surface, this is going to be the normal force. So we know the normal force associated with each number of textbooks. And you can see here, as we increase the number of textbooks, the normal force, or the surface force, increases. Now, as you'd expect, the applied force is also going to be impacted. So if we have one textbook, let's say we have to pull with a force of 4 newtons to overcome 4 newtons of friction. If I have two textbooks, we saw in class, we required double that amount. So the friction would double, therefore I have to apply double the force applied to overcome the friction. And we see this pattern continue. So again, this is from the mini lab that we did in class today. So when we look at the trends that we see with the data, we saw that as the normal force increases, the surface force increases, the force of friction increases. And it increases at the same rate. If you double the normal force, the force of friction doubles. You make the force normal 5 times larger, friction becomes 5 times larger. So we can say here that there's a direct relationship between the force of friction and the normal force. Okay, now the next part is what is looking at the relationship between friction and normal. I'm going to be looking at a ratio. So we're going to be looking at the force of friction relative to the surface force, or the normal force. So we'll be dividing these two quantities, and that's in this last column over here. So when we look at the values, for the first one textbook, we have a force of friction of 4 newtons. The normal force was 11. So 4 over 11 is going to give us 0.36. And you notice that the units cancel, so we end up with 0.36. And what this really represents is telling us that friction is 0.36 of the normal, or 36% of the normal. When we do this, when we have 2 textbooks, we have 8 over 22, and we end up with the same value. And you do that for all of the remaining textbook combinations. You'll notice that this ratio remains constant. It's a constant ratio. So it's saying that the force of friction is 36% of the force normal, or the surface force, for this particular textbook on this particular surface. So the trends that we see in the data, we see that as the normal force increases, the force of friction increases. And we saw that the ratio of force of friction to the normal is constant. It's a constant ratio. And we find that experimentally, if you look at this in the real world, every surface pair combination has a constant ratio. So if I looked at, say, a wooden block on the desktop surface, it would have a constant ratio. It's not going to be 0.36, but it would be constant for any combination of masses. Now this ratio is a special significance. It's called the coefficient of friction, and we give it the symbol mu, the Greek letter mu. And the coefficient of friction is constant, as I said, for any two surfaces, and it represents the ratio of force friction to force normal. So we can write an equation, actually. So the coefficient of friction is equal to the force of friction over the normal force. So remember, this value, the coefficient of friction, is constant for a given pair of surfaces. And the reason is, as the force friction increases, force normal increases at a corresponding rate. So this ratio is always constant. Okay, this next little bit is directly from your textbook. I just want to emphasize something with the coefficient of friction. So the coefficient of friction, or the U value, between an object and a surface only depends on the type of materials. The thing you have to be careful with is the results can sometimes be affected by the condition of the surface. So it means cleanliness, if the surface is wet or dry, if there are any imperfections in the surface. So all of these might make a little bit of an impact on the data. But nonetheless, you can actually look up the coefficient of friction between different surface pairs or different surface combinations. And sometimes they're even given as ranges to take into account the slight imperfections that might be present. So for example, you can look up rubber on dry concrete, and you see that the coefficient of friction, and this is mu k, the kinetic friction, varies from about 0.6 to 0.85. Now when you look at rubber on wet concrete, the coefficient of friction is a little bit lower, which means that there's a little bit less friction. So the friction is less of the normal force. And it makes sense. When you have wet concrete, it's harder to stop. Your tires can't grip as much. We can also look at rubber on ice. It's a very icy day, and the value is 0.005. So it's a very, very low coefficient of friction. So it tells you that there's very little friction when it comes to having rubber on ice. So the mu k value, just to kind of summarize here, as the mu k increases, the force of friction for a given surface and given mass will increase as well. So it gives you a rough idea of the amount of friction that's present. And then what you can do is you can calculate the actual amount of friction using this equation. So I can plug in a number for the coefficient of friction. So I'd have this. Force of friction is equal to coefficient of friction times my force normal. And if you look carefully, there's a cool hidden code in here. Friction is fun. So F-U-N. Friction is lots of fun. It's a neat little thing. Okay, so let's summarize what we've done so far. So far we know that we have the static friction. It's a force of friction preventing two surfaces sliding against each other, so it prevents the motion. Kinetic friction is when you have a force exerted by a moving object on a surface, so the surface is opposing the motion of the object, and it's acting the opposite direction. We also have the coefficient of friction. The coefficient of friction we saw was the ratio of the force of friction to the normal force. And you can have a coefficient of static friction, which is the maximum amount of force required to move an object, to start moving an object. You can also have the coefficient of kinetic friction, the amount of force required to move an object, an existing moving object on a surface. So again, this coefficient is constant. Very important you recognize this. But the force can vary. The force varies depending on the mass of the object.